Hello everyone, and thank you for watching my video today. And in this video today, we're going to talk about defining convergent and divergent infinite series. But before we do that, we have to do quite the review on sequences and series from what you hopefully learned in your Algebra 2 or pre-calc days. So let's start here with the basics. Consider the following list of numbers that we see right here. How would this list be generated? Okay, this list is an example of a sequence where each number is called a term of the sequence. We can denote them in three different ways. Well, there's a lot of different ways, but these are three different ways we do that. The subscript that appears in the sequence is called an index and indicates the order of the terms in the sequence. The sequence often starts with an index of 1, but could be 0, could really be anything. It's up to the person who's making this sequence. There are two ways to define a sequence as illustrated on the next table here. Implicit versus explicit. Implicit is also called recursive. So recursive means each term is in the sequence is 3 more than the preceding term. So it's defined according to the previous term. So this would be called the next term. A sub n plus 1 equals a sub n plus 3. Okay? This would be our implicit formula right here. Explicit is usually only good. It's really good if it's an arithmetic or a geometric sequence that we're looking at here. In this case, this is an arithmetic one where the numbers are going up by the same number every time. Usually you can look at that in slope-intercept form to look like that, where the slope is just the number that's going up or down by each time. Okay? There's benefits and drawbacks to each. The benefits and drawbacks are listed there. For implicit, it's usually easy to see the relationship, but it's not very helpful if we want to find a large term, like, say, 50. For explicit, the benefit can be we can find any term really quickly, but the relationship could be a little bit difficult to see, especially if it's not arithmetic or geometric. So let's take a look at a couple explicit formulas here. So our first explicit formula would be 1 over 2 to the n throughout the first 4 terms. Okay? So a sub 1 would be 1 over 2 to the 1, or 1/2. A sub 2 is 1 over 2 squared, or 1 to the 4th. Sorry, 1/4. A sub 3 is 1 over 8. And a sub 4 equals 1 over 2 to the 4th, or 16. For b, a little bit harder here. So a sub 1, if we put a 1 there, we get negative 1 times 1, so negative 1, over 1 plus 1, or 2, so negative 1/2. A sub 2 would be negative 1 squared times 2, which is 2, over 2 squared plus 1, which is 5. A sub 3 is negative 1 cubed times 3, so negative 3 over 10. And a sub 4 is negative 1 to the 4th times 4, so 4 over 17. If you were to graph these are what the two sequences would look like on a graph. And obviously I went a little bit past the first 4 terms there, but you can see how they kind of differ, how they're the same and kind of differ at the same time. All right, working with some sequences for each of the following. Find the next 2 terms, a recursive definition, and an explicit formula as well. All right, so this one looks like we're adding 7 every time. So this would be called an arithmetic sequence, in case you don't remember that. The next 2 terms would be 26 and 33. We're just adding 7 every time. All right, so recursively, we'd write this as a sub 1 equals negative 2, and a sub n plus 1 equals a sub n plus 7. Okay, and then explicitly, since the slope is 7, all right, we can just write this in the arithmetic formula, which would be the first term, which is negative 2 plus n minus 1 times the difference. And if you simplify that, you get negative 2 plus 7n minus 7, or 7n minus 9. Next sequence looks like we're multiplying by 2 different times. So this is called geometric when we're multiplying by the same number every time. So next 2 terms would be 96 and 192. All right, so a recursive formula, so b sub 1 equals 3, and then b sub n plus 1 would be 2b sub n. We're just multiplying by 2 every time. Then an explicit formula, for those of you that may not remember the explicit formula for geometric, it's just the first term times the common ratio to the n minus 1. All right, let's bring on some calculus here. The limit of a sequence. The limit of a sequence can be written as limit as n approaches infinity of the sequence is equal to L, as long as L is a unique number as n increases. Okay? That's all this is saying here. Again, is we're just trying to look for the limit of these. And this is really what we're going to be doing a lot in this chapter in general, just trying to find if these sequences converge to some limit or not. All right, so our example 3 says, for each of the following sequences, write out the first 4 terms. If you believe the sequence converges, make a conjecture. If it diverges, explain why. Assume each sequence has a beginning index of n equals 1. All right, so we're asked to find the first 4 terms. So for A, our first term is negative 1/2. Our second term would be 1 over 5. Our third term would be negative 1 over 10. And our fourth term would be 1 over 17, looks like. Okay. So what are these numbers getting closer and closer to? Negative 1/2, 1/5, negative 1/10. Yes, they are jumping back and forth to be positive, negative, but on both sides of it, they're getting closer and closer to the same number. As the denominator gets bigger, our answer is actually getting closer to 0. So we would say this converges to 0 because the limit as n approaches infinity of a sub n, sorry about the bad squigglies, looks like it's plus or minus 1 over infinity, which is 0. Second one, all right, b sub 1, so cosine of pi, negative 1. B sub 2, cosine of 2 pi, 1. B sub 3, cosine of 3 pi, negative 1. B sub 4, cosine of 4 pi, it's 1. So this is just going to alternate back and forth between negative 1 and 1. This is never getting closer and closer to any specific number. It's going to go back and forth. So we would say this diverges. Okay, why? Again, because it looks like all it's doing is alternating between 1 and negative 1. So the limit would not exist. Okay. Third one, c sub 1 would be 4 times 1 over 1 plus 1. So 4 over 2, which is 2. C sub 2 would be 4 times 8, which is 32 over 9. C sub 3 would be 4 times 3 cubed. Might be time to get the calculator out here. 4 times 3 cubed, which is 4 times 27, over 3 cubed plus 1, which is 28. So 108 over 28. And c sub 4 would be 4 times 4 cubed, which is 256, over 4 cubed plus 1, which is 65. All right, looking at this, I don't know if this converges or diverges or not. So let's see, we got 2, and then 32 over 9 would be 3.556. 108 over 28 would be 3.857. 256 over 65 would be 3.938. Now we're getting a pretty good picture. Looks like this is getting closer and closer and closer to 4. So my guess is going to be this converges to 4 because it looks like the limit as n approaches infinity of c sub n is going to be 4. Now we probably can use some calculus to actually figure that out. If we took the limit as this approaches infinity, we wouldn't get an answer, but there's something we can use from back in the day. If you remember, L'Hopital's rule. If we took the derivative of the top and bottom until we could put infinity in, we would end up getting our answer of 4. All right, and the last one here. So d sub 1, we don't know, but d sub 2 would be negative 2 times d sub 1. D sub 3 would be negative 2 times d sub 2, which is negative 2 times negative 2 times d sub 1, which is 4 d sub 1. And d sub 4 would be negative 2 times d sub 3, which is negative 2 times 4 d sub 1, which is negative 8 d sub 1. So basically, we're just going to take d sub 1 and multiply it by negative 2, then times 4, then times negative 8. This looks like it's going to be diverging, because we're not going to be getting closer and closer to some specific number as we get bigger and bigger. Next one, a bouncing basketball. A basketball is tossed straight up in the air, reaches a high point before falling to the earth, falling to the floor. Each time it bounces, it rebounds to 0.6 of its previous height. This sounds like a geometric sequence. Let h sub n be the high point, up to the nth bounce, with initial height being 20 feet. Find the recursive definition and an explicit formula. All right, so the recursive definition would be h sub 1 equals 20, and h sub n plus 1 would equal to 0.6 h sub n. And an explicit formula would be 20 times 0.6 to the n minus 1. So again, recursive, explicit. B, what is the high point after the 10th bounce? We can use either one, but this one definitely looks like it'd be a lot easier to use. So we're going to look for h of 10 equals 20 times 0.6 to the 9. Definitely use your calculator for that. So 0.6 to the 9th times 20. The height would be 0.202. What is this, feet? Yeah, it's feet. It took me a while to find that, but it's feet. All right, what conjecture can we make about the limit? Well, if it's going to keep multiplied by 0.6, it's going to be getting smaller and smaller and smaller. So my conjecture is the limit as n goes to infinity of h sub n is going to go to 0. All right. Infinite series and the sequence of partial sums. This slide basically just says if there's a way that we can find out an answer for an infinite limit. Okay, so we're talking about some square here with sides like the 1. All right, we're going to keep multiplying it by half and see if we can come up with some type of conjecture for its limit. So the first one, we color in half of it, we get 1/2. Then we add half of what's left over. Then we add half of what's left over, and half what's left over, and half what's left over, forever and forever and ever. We're never going to actually get an answer of 1, but it's going to get really, really, really close to 1. At some point, it's going to be so close to 1, we're just going to call it 1, even though it will never actually cover in the entire square. It's going to be so close to 1 that we're just going to say it's 1. Okay? So therefore, we'd say that the sum approaches the entire area of the square, which is 1. We can say that the limit of s sub n, as n goes to infinity, would just be 1. All right, and then we're going to talk about the definition here of an infinite series, which is kind of what that's talking about here. Even if it's not going to actually be an answer, we can figure out its limit. So given a sequence of numbers with this sum is an infinite series. Its sequence of partial sums has the terms like this. Or we could just say that. If the sequence of partial sums has a limit L, this infinite series converges to that limit. And we can write that this equals that limit L. If the sequence of partial sums diverges, then the infinite series also diverges. All right, so let's talk here about this slide. Consider this infinite series. So we have an infinite series here. We know it's going to infinity. Find the first 4 terms of the partial sums. All right, so s sub 1 is going to be our sum from 1 to 1 of 1 over k times k plus 1. So we put 1 in, we get 1 over 1 times 2, which is 1/2. Okay? So now, sum of the first 2 terms, we're going to change that to 2. So if we put 1 and 2, if we put 1 in, we get 1/2. If we put 2 in, we get 1 over 2 times 3, which is 1/6. So 1/2 plus 1/6 is 4/6, which is 2/3. All right. and about my 3. All right, so that's just going to be 1/2 plus 1/6 plus, if you put 3 in there, we get 1 over 3 times 4, so 1/12. So 1/2 plus 1/6 plus 1/12, some quick math where we should get 9/12, which is 3/4. All right, one more time. The first 4 terms. So now we're going to add 1/2 plus 1/6 plus 1/12 plus 1 over 4 times 5, which is 1/20. All right, the common denominator would be 60. Add those all up, we should get 48 over 60, which is 4/5. Find an expression S sub n and make a conjecture about the value of the series. All right, so S sub 1 would be 1/2, S sub 2 is 2/3, S sub 3 is 3/4, S sub 4 is 4/5. Looks like the conjecture, so the limit as n approaches infinity of S sub n is just going to be, the numerator looks just like it's going to be n, the denominator is just going to be, I forgot to write my limit again there, okay. Limit of n goes to infinity, and the denominator is going to be 1 higher than n, so n plus 1. And we talked about L'Hopital's rule earlier, right? You can't, right now we get infinity over infinity, but if we take our derivatives, we get limit as n approaches infinity of 1 over 1, which is 1. So it's never going to actually be 1, but it's going to get closer and closer and closer to 1. Okay? All right, the last thing, we're going to graph these two on our calculators. Consider the following a sequence and its series. The graph, so we're going to graph each and find its limit. The graph of the sequence is pretty straightforward. We're just going to go to our graph, and we're going to type in, I'll get rid of all this here, x over 2x plus 1. My window, I'm going to go from -1 to, let's go, I don't know, 20. And my y's, I'm going to go -1 to, it's going to be pretty small here. Let's go 2. All right, it looks like the limit is getting closer and closer and closer to 0.5. So if I was to guess there, I would say the limit is getting closer and closer and closer to 1/2, which makes sense because if we were to put infinity in, we would get infinity over infinity. Taking our derivatives, we would get 1 over 2, which is 1/2. Now, to graph its series, this is a little complicated. Try to follow along here. Get your calculator out if you don't already. First, we got to go to mode, and you got to scroll down to sequence mode. Scroll over to sequence mode there. I'll go to y equals. And it looks like this calculator does not work with sequence mode. Okay, well, I'll try to explain it to you in words. And if you need help, you can always come see me later on. So scroll down to mode and go to sequence mode, then hit y equals. And you should see n min, u of n, and u min. All right, for n min, it's almost always 1. That's the starting index there. So that generally just starts with 1. For u of n, you're going to type in the sum of the sequence of n over 2n plus 1. So if you don't remember where that's located, you go to second statistics, scroll to math. Number 5 is sum. Now remember, this is all in the y equals menu here. Then second stat, scroll to operations, and number 5 is sequence. And then if you have a newer calculator, you'll see this come up. You type in your function here, which is n over 2n plus 1. The variable is going to be n, and you're going to start from 1, and you're going to end at n. And if you graph that, you should see basically something that looks like a line with a slope of 1, but that line goes up forever. So your graph is going to look something kind of like this. So our limit's going to be infinite. Okay? I can show you that more in person if you need a little bit more explanation with that. All right, but otherwise, that's it for today's lesson. I hope you enjoyed our first look into Convergent and Divergent infinite series. Thanks again for watching my video, and we'll see you again next time.